to host her because Hilke has just, over the past, probably a couple decades now, just done incredibly creative and rigorous work, both inside and outside the solar system, our planetary system and other planetary systems. And I've just enjoyed reading your papers and then thinking about your theoretical thoughts and how we might observe them. And we're so delighted to have you visit here today. So let's please welcome Professor Schlichting.
Thank you very much, Dave, for this very kind introduction. Thank you, everyone, for coming. It's really a great pleasure to be here. And I guess I would like to take the next sort of 50 minutes or so to tell you a little bit about the things that have been keeping me up at night and sort of excited, related to extrasolar planets and planets in general, and what I think we can learn going forward. I would like to say, I don't have a specific agenda to necessarily go through all the slides in great detail. So if I confuse you and you have a small question in between the talk, please feel free to raise your hand and ask. I'd rather have you all follow along and get something useful out of it than me giving you a monologue, okay? Of course, I will leave time for questions at the end as well. But especially if I lose you along the way and I use some term that you never heard before, please do ask. Okay, so here we go. So as I'm sure many of you know, exoplanets has been the super interesting field over the last sort of decade and more. And I think the thing that for me has been most intriguing is this new population of planets that was discovered that we now call super-Earths and sub-Neptunes, that are planets in size in between what we have in the solar system, right? They're bigger than Earth and smaller than Neptune. We don't have a single planet like this in our own solar system. They also live in an orbital period space where we have 0 planets, right? They are so far mostly discovered within 90 days, so inside the equivalent of Mercury's orbit. And the universe makes loads of them, or at least our galaxy has loads of them. So it's a super intriguing population. And for somebody like me, I'm really interested in understanding the formation of planets. That poses a super interesting challenge. So how did they form? How should we think of them? And where did they come from? So generally speaking, what we have learned so far is that so there are these 2 populations, and we call the smaller ones now super-Earths, and the bigger ones sub-Neptunes. And generally speaking, these super-Earths that will be focus of the second half of my talk, they are to first order look like an average density bulk composition similar to a rocky type Earth planet. And the ones up here typically require some sort of light element, we think most likely hydrogen, in sort of atmosphere on top to explain their radius given their mass on a population sense. And then so intriguingly, these 2 populations are divided in sort of planet size or period space. Also, if you plot it in planet size stellar mass space, and I'll come back to this. But let's start by just asking this question, what do these planets look like? What are they like? And specifically, if we can start observing their spectra, which is, I think, one of the really exciting new developments, especially with James Webb, what does it tell us about the planet? So this is probably the nicest of sort of a sub-Neptune spectrum here, TOI 270d. You can see all these spectral features. And what's very interesting, so this is what we would call a sub-Neptune. It has an estimated mass of 5 Earth masses, a radius about twice the radius of the Earth. If you do a very simple model of just putting a core, a mantle, and a hydrogen envelope on top, you will infer that this corresponds to roughly having 2% by mass and hydrogen. So it's good to remember throughout my talk, these planets, although the sub-Neptunes often have a hydrogen envelope that we can probe, their mass is dominated by rock and metal, right? Hydrogen is by mass, it's just a small fraction, but it matters because it gives you a significant larger radius. And hence lets us probe their envelopes, their composition. And so what's been inferred about this from the spectrum is that the mean molecular weight is actually roughly 5. So it's more than just hydrogen and helium, more than twice of what you expect for that. And that the atmospheric metal mass fraction, so anything other than hydrogen and helium, is about 50 or 60% by weight. And the most prominent species are methane, CO2, and water. So the question to me is like, what does it mean? What does it really tell us about the planet? I think it's awesome that we can detect this, but what does it mean, right? Because we're probing the less than 2% mass of the planet, just the sprinkling of the atmosphere, the upper envelope. What does it tell us about the rest of the planet? Or does it tell us anything? And so we took a step back and asked, how do these planets form? And I don't want to spend the whole talk talking about their formation. This is just sort of to give you a cartoon overview. Right? Let's imagine you have a little core in the disk, and eventually, right, it becomes large enough that it can gravitationally hold on to the atmosphere. And so how large is that? It's basically when the physical size of the planet is smaller than the Bondi radius, right? The Bondi radius is a distance up to which your gas molecules would be gravitationally bound to you. As a fun fact, in the solar system at 1 AU, this is roughly the size of Ceres. So Ceres was just sort of on the limit of accreting a little bit of hydrogen from the nebula. If you then grow to larger masses, you can hold on to more and more gas. And why am I going through this? Is because one really important corollary is that these cores are actually extremely hot from formation. That's because, right, when you assemble the planet, you can convert a lot of basically kinetic energy or gravitational energy into heat, right? Because you need to form a bound object. So you have to get rid of that energy thermally. And you do that. And initially, if you have too much heat, you will just radiate it away and you can't hold on to the gas. But as soon as you lost enough of this energy that you're cool enough for the hydrogen to become gravitationally bound to you, you will basically trap that heat because you start accreting an optically thick envelope. And so now, right, your core that in isolation would have radiated away into space in like a couple of thousand years and be cold. Now, because it has an optically thick hydrogen helium dominated envelope, it will take gigayears to cool to like 1,000 Kelvin or less. So that's one of those. These planets are hot on the interior. And this is maybe not so surprising because if you know anything about Uranus and Neptune, they're also still thousands of degrees of Kelvin on the inside, although we think of them as ice giants. So then the question that, came to my mind was like, well, what does it actually mean about the planet? So this is how, I used to think about planets. And I think it's probably true for most astrophysicists. You have like, an iron core, a silicate mantle, and then some gas on top, and they're discrete layers, and we don't have to worry too. It's like a physics problem. It's easy. That's it. But the reality is, so if this is now a structure of one of those sub-Neptunes roughly modeled on TY 270d after a gigayear, so after it's already a gigayear old, you see that its interior temperature is still around 5,000 to 6,000 Kelvin at the interface between the atmosphere and the silicate mantle, which is in fact molten, which is like a magma ocean, and even higher if you would have a discrete metal core. It's not even clear that these would be separated. And the interface at which they're interacting is at several gigapascals, so pretty high pressures. So then the question is, what would actually happen, right? So from a physical point of view, you may say, oh, nothing, our models were fine, but it's not true, right? In terms of chemistry, loads of things will happen because hydrogen is extremely reactive and will interact chemically with the magma ocean. And so this is basically the question then that we had is like, what kind of state would this planet be? So we tried to ask the simplest question possible, which to me was still pretty hard because it includes chemistry, and chemistry is a lot harder than physics, in my opinion. So the question then was like, what would be the chemical equilibrium state of a planet that has molten metal, a magma ocean, and a hydrogen-rich envelope? What would it be like? What is in the atmosphere? What's in the interior? What are the implications for its composition and the evolution? So loads of interesting effects can happen, as I will delve into. And then most importantly, I think, what does a planet's atmospheric composition really reveal about the interior, right? What can we really learn by probing the 1% of the atmosphere, or even less than that? So with these questions in mind, we embarked on this exercise of making a global chemical equilibrium model. So I'm sure many of you know about chemical equilibrium. So global here means that we really let the magma ocean interact with a hydrogen envelope and the molten metal. So those three states can interact with each other chemically, and we're just finding the chemical equilibrium state as the very first order approximation to this problem. And then in the very first iteration of this model, we included 7 distinct chemical species listed here, and then 25 different phase components, because of course they can exist in different phases, and of course they also exist like in the gas phase and the molten phase and so on and so forth. And then they could be characterized by 18 independent reactions. And if you know anything about global chemical equilibrium models, one of the beauties is that because it's a global chemical equilibrium model, it does not matter which specific equations you write down to solve, as long as you find an independent basis set, because you can reconstruct all the other subsets of reactions from that by linear combinations. So anyway, so once you've done that, it's like a matrix inversion problem, which, you know, is a little bit annoying, but very doable. And so basically we use this then to determine what the composition of the envelope would be, the interior and the core. And I just want to share like a few example results with you, just to get an idea of what could happen. So let's start with TRI 270D, because that was sort of one of the motivations to do this. So if we now look just at the envelope, and only the upper parts of the envelope, that's basically what we find. So you find in composition and by weight percent, depending now exactly on what the true temperature is, where the hydrogen is interacting with the magma ocean, for 4,000 Kelvin, you still find a hydrogen-dominated envelope by mass, but a lot of methane and about a couple of % of water being produced. If the temperature is a little bit higher, you can see that you actually transition from being hydrogen-dominated to methane and CO-dominated. So to zero order, I thought this was quite encouraging, because you can start to see that you can explain sort of a mean molecular weight in the right range, the sort of right bulk atmospheric metal mass fractions. And I think it opens a way for us forward to use the atmospheric composition that we can observe to actually learn something about what's going on the planet. So it's like the first time we have like a physical model that's connecting the true interior of the planet, that's like 95% of the mass, to something we observe, right? Before, you know, I don't want to give not enough credit to the observers. It's great, right? We can measure what is there, but we fit spectral lines without, you know, any inference from how they were made or where they come from. We just look what is there. So now we can take it one step further and try to connect it to some underlying planet properties. So this is the very beginning. So the idea, of course, is now to make a library and extend this to many planets. But I think it's a promising avenue for the future. And one thing that I'll come back to again and again is that you always produce a couple of % of water. So the hydrogen magma ocean interaction is very good at making water, at least if a few % by mass is what you're after. Okay, so me as a theorist, I was pretty happy with this. But then, of course, this is just for the bulk of the envelope. We want to do a one-to-one comparison with the observations, right? And so this was taken one step further by some work that actually Matt Nixon led. So now you can take our composition from the global chemical equilibrium model that is sort of at the base of the envelope, and then self-consistently solve, for the pressure and temperature profile of the atmosphere, doing, again, equilibrium chemistry at the different heights and different pressures, and then also accounting for rain out and condensation. So you go through this, and you have to do this iteratively until you find a fully self-consistent solution. And this here was done by coupling Helios with, I think, fast chem condensation. And then once you have that, you have to still then do photochemistry at the very top to allow for the irradiation from the star. But if you've done all that, you have a true profile of abundances of height in the atmosphere, and you get something like this. So this was the abundances predicted just from the global chemical equilibrium model at the base of the envelope. And now you can see how their abundances would change with height. So, you know, typically we observe somewhere in this range here. So you can see some obvious candidates. Potassium will condense out, so we probably won't be able to access this observationally, at least for this planet. But water, methane, CO, they're all here. And then these errors are actually the values estimated from observations. So I think it's actually quite promising, quite interesting. You can take it one step further. Still, of course, now this is nice, but what you really now can do is you can make a spectrum from this, and this is what is shown here. So the yellow is the data, and then for this purpose, it really doesn't matter which one you pick, either the blue or the reddish color. They're basically the same. And you can see, so the model predictions are this continuous line, and the data is in yellow. And I think, I mean, I'm biased, but I think that's a pretty great match. So I think we can say for TI-270D, certainly magma-ocean interactions are fully consistent with the observed atmospheric spectrum of this planet. And this is the first, and we have a lot more work to do, but I'm personally quite hopeful that this will be a very fruitful way to go forward in this discipline, especially with the sub-Neptunes, because there will be more to come. Any questions before I go on? Yes?
Can you apply this to K2 APB?
No, but we will.
I have a question. So,
Yeah.
This is an equilibrium model.
Yes.
So do you have to worry about the time scales for these diffusions? Is that something that is included or not? Does it matter?
So it's included. So let me take one step. So it's an equilibrium model in the sense that how the atmosphere, the interior, like the metal and the silicates equilibrate, like determining that chemistry and what's at the base of the atmosphere. And those time scales are very short because it's so hot. But then if you go higher up in the atmosphere and you translate it to an observable spectrum, you do have to account, this is in the last step here, the diffusion across the radiative convective boundary and the photochemistry. So the diffusion part that really matters, which is usually high up when you transition sort of from the fully convective part to the radiative part, because there the transport is less efficient, that's included here. Yeah.
Thank you.
Yeah, you're welcome.
There's this little line at 4.5 microns, sorry, on the next slide. That does look consistent with the model emission. Should I look into that at all? What is it?
I should, but I don't know.
Oh, that's it. Okay.
Yeah, there's also there's claims now for a sodium line that I would like to check out, and we haven't yet included sodium, unfortunately, in our. Did I say something wrong?
No, I said I love sodium in exoplanets.
Yeah.
I wasn't meant to say
Yeah, so. But we just when we made this model, we were just very naive, and this would be one of the species we definitely should have included. We haven't yet, but we are currently working on it. So that'd be something else, I think, to include, and that we should be able to pull out of these envelopes. So it's really a very active work in progress. Okay, yeah, go ahead.
You're not going to get past the slide. This is it. I just want to make sure I understand the model. So the chemistry part I understand. I mean, not really, but basically, what are the knobs that you're varying here? Like, are you fitting for the mantle atmosphere temperature and the core mantle temperature? Is that what I gather those terms are? I kind of miss what's the underlying structure that you're.
So I would tell you we're not really fitting for anything, but.
So what's the connection between the structure and?
So the structure. Okay, so it's true. You have to assume a temperature of the magma ocean interacting with the envelope. The good thing is actually we are now through experiments know much better what that should be, because it's like what's called at a Solvis temperature. So it's roughly 4,000 Kelvin, and you can change that, and you would get slightly different abundances. In fact, I'm not sure the spectrum would change that much, because spectra are not that good typically at measuring absolute abundances. And the structure was determined from a formation model that then let the planet cool to its current age. So from that, you get like the temperature pressure profile and the interior temperature. But then it was solved again self-consistently once you had the chemical equilibrium to account for like rain out and so on and so forth to connect it to observations. Yeah, it's like a multiple step. Yeah.
Letting it cool.
Yeah. Okay, I don't know who was first, but like Matt, why don't you?
Yeah, so I have a question about how much you're modeling the interior makes it matter. Just to follow on to that.
Yeah, so the interior, so the big assumption is that all these reservoirs can fully exchange chemically with each other. That's the assumption. Whether or not that's fully true, that's a different question. And I think worth looking into. Yeah, let's do, and then we go up.
Composition of the envelope, then the ability to radiate energy away changes.
Yes,
So is that part of your model, or at 4,000 K doesn't matter?
yes. It's part of the model, but the fact is where you radiate away the energy is only at the upper part of the atmosphere, because this is where the envelope becomes optically thin. And so we account for that from what is present here in terms of chemistry. Yeah. But yeah, you don't radiate away the energy at 4,000 Kelvin, because I haven't been out. And there was one more, yes.
So this is a more basic question and goes back to our sort of how I understood these models from about 20 years ago, which was when you get to the bottom, you have an atmosphere, and as you get down and down in that atmosphere, the atmosphere is under great pressure and begins to act more as a solid, as an ice. And then you work up from the bottom and you have the magma ocean. So does an ice layer play into this, or is it sort of the same as the magma ocean now?
Yeah, so there's no ice layer in this. I think it's too hot to support that. But we do account for the different phases you can be in. So like one thing we're including right now is miscibility. So if you reach high enough temperatures and pressures, hydrogen and silicate or hydrogen and water, they become fully miscible, meaning you can mix them at all proportions. And that's probably the true way of defining this magma ocean temperature. Yeah.
Right, okay.
And that's super interesting, and I'd love to tell you more about this, but that will be a whole other colloquium. So maybe in a couple of years we can do it. Okay, let's move on. Well, one small side note that I think is quite interesting and that definitely deserves more work, right? I think thanks to Karen, we know the importance of disk chemistry in forming planets. I think the point I'm trying, that I would like to make here is that I think at least for sub-Neptunes, like for smaller planets that only have a few percent mass sort of from the original disk and hydrogen helium, I think the planet's chemistry also now matters a lot for for what you see. So one example here I picked is the C/O ratio. So what this shows you is the C/O ratio in the atmosphere compared to the mass of the planet in the atmosphere. So 2% to 10%. And then this is the C/O ratio from the disk and the assumed C/O ratio from the core. This is just like based on Earth, basically. And this is just to show you that the chemistry of the envelope interacting with the magma ocean can completely overwhelm, if you wish, the original C/O ratio that you may have gotten from the disk. So it's a word of caution. I think for gas giants where the mass budget is all in hydrogen and helium, I don't think any planetary chemistry can overwhelm the signature from the disk. But I think for these smaller planets, we need to be more cautious because the interior planetary chemistry can actually erase the signature. So it's just a small side, but I think it's worth thinking about. Okay, so these were my stuff for the sub-Neptunes. Let's talk a little bit about the super Earths, so the smaller planets that sort of look rocky. I think the most intriguing thing that I learned, I think, from them is the best that I can tell is that as a population, the super Earths may have been born as sub-Neptunes. So that means they were formed with a hydrogen helium envelope that then was lost over time. Not all of them, but I think as a population, we have several lines of evidence that sort of tell us that. And at least what I find intriguing is there's a couple of observations that basically look at the abundance of super Earths relative to sub-Neptune. So when you look at the number, the relative number, if you wish, of super Earths relative to sub-Neptunes around younger stars, so younger than a giga-year, there is fewer super Earths relative to sub-Neptunes. And then if you do a similar population study around older stars, you find that the relative abundance is increased. So it's suggesting that these super Earths are being formed on giga-year timescales. These are very hard things to do. It's like complicated corrections that you have to do for your samples, but it's intriguing. There's a couple of studies now that find those results. We also actually see some of these planets lose their envelopes in real time. So this is there's actually several results on this. It started out to be typically more sort of for the hot Jupiters, but over time we've worked our way down to smaller and smaller planets. And most recently, this has been one of my favorite systems. So TOI 776 B and C, so it's 2 planets in the system. And I've been part of a collaboration that had some observations with HST looking for these planets losing their envelopes using Lyman alpha transits. And indeed, they seem to be in Lyman alpha transit for both of them, one better than the other. But we do seem to see atmospheric loss happen in real time of a system that's sort of like, a few gigayears old. So we have, at least for a very small number of planets, some direct evidence of mass loss. And then on a population level, we can do some modeling that I think is also pointing towards having been born as one population and then losing the envelopes, basically through hydrodynamic escape. So they've been traditionally 2 sort of theories that explain how you drive the hydrodynamic escape. But the idea is you have hydrodynamic escape of the envelope of the lower mass planets that are closer in, where the envelope is less strongly bound. So what powers this escape? So there are 2 things. One is photoevaporation, so it's just a high energy radiation from the star that's heating the upper envelope, driving the escape. And then core part mass loss, which was in large part developed by my group. It's the internal energy, especially the heat from formation, that's still helping lift the material out of the envelope together with the bolometric luminosity of the star. So you don't need necessarily the high energy radiation. And we used to write all these papers showing that you can match the observations quite well, explaining sort of this radius valley of these populations in these different parameter spaces. But of course, in reality, both of these should be happening. And we have since joined forces and developed a model that includes both photoevaporation and core part mass loss. And it's very cute. You can show that in different parts of parameter space, one dominates over the other. And so often planets start out in core part mass loss and then transition into photoevaporation throughout the evolution. So anyway, so on a population level, I think hydrodynamic escape, let's ignore the details, it doesn't matter, can explain quite well on a population level these 2 planets. So all this is to say, all this is just to motivate what would the implications? So if we find all these rocky planets, and they all started out having a history with a hydrogen helium dominated envelope, what does it mean for the habitability or for the type of planet they are? I mean, doesn't it matter? We don't care. Does it have some interesting implications that we can test? Does it matter for wanting to search for life one day? So there are a couple of things that I think can be preserved. So one thing is related to the core, to the metal part of the planet. So hydrogen is extremely siderophile, meaning it's ion-loving. And so these planets, these super-Earths, when they were sub-Neptunes and had the hydrogen interact with the molten magma and the metal melt, incorporates a lot of hydrogen in the interior. So by mass, this is now the composition of the metal core. But the mass fraction is still dominated by iron, which is this blue here, and it's only a small percentage by mass and hydrogen, silicate, and oxygen shown here, a few percent. However, if you ask in terms of number or mole fraction, hydrogen actually dominates over metal in this case already. And you see it's pretty similar result across like typical super Earth masses from 1 to 10 Earth masses. So that's very interesting. So what this implies, though, then, because hydrogen in particular is so much lighter than iron, is that you form underdense cores. So so the super Earth lost its hydrogen envelope, but because you couldn't take the hydrogen, especially from the metal phase, back out of the planet, it's like preserved as a signature. And so the bulk densities of the planets should on average be somewhat less dense than you would expect for a pure iron core. And this is, of course, extremely hard to probe for a population, because I'm sure most of you know the mass radius diagram is like full of degeneracies. We only have 2 measured things, and you can explain in many ways. But nonetheless, if you look at this population and plot this normalized density that's normalized to Earth, and this is basically the super Earth population, the 1 sigma contour and the 3 sigma contour, you can see it's on a population level slightly underdense, about 10% underdense. So closer to 5 grams per centimeter cube rather than 5.5, which Earth would be. And the model results sort of fall nicely in the middle. So it's no proof, but it would be one other piece that sort of hangs together with this idea that maybe the super Earth had a hydrogen envelope in the past that left this chemical signature. The other, I think, interesting point, especially for the super Earths, is the water production. I already mentioned, right, that hydrogen interacting with a magma ocean produces a lot of water. I mean, a lot meaning maybe a few % by mass. For me, that's a lot. It's definitely a lot more than Earth has. And again, so this is just for a super Earth starting out as a sub-Neptune, then that hydrogen envelope being lost, and you constantly re-equilibrate chemically until you have cooled enough. So you need to do a formation and evolution model together with the chemical model until you cooled enough that you basically solidify the magma ocean, and this exchange is no longer possible. And then you can ask, what is that chemical end state of this planet? And how much water do you have and where is it? And so this is what we did here. So this is basically in Earth oceans. So 1 Earth ocean would be here, 10 Earth oceans would be here, 100 Earth oceans would be here. And this is planet mass from 1 to 10 Earth masses. And then you can see, I told you already, most of the, in this case, hydrogen, oxygen actually will be in the metal melt phase. So I think we can ignore this part because you probably cannot access this again. This will give you the underdense cores, but other than that, it's probably not very helpful if you want some fish swimming around in your ocean. So let's ignore this. But I think interestingly, you get about 10 Earth oceans worth of water in the planetary envelopes. And this is great because if the planet would cool enough, and if it's the right distance from the host stars, this will rain down and become an ocean, a surface ocean. If it's too hot, it will stay as vapor or steam in the atmosphere. But if you're at the right distance and your planet can cool enough, this would sort of rain out. And then you also have in the silicate melt another sort of 1 to 10 oceans worth of water, and that you can probably also tap into through outgassing and volcanism and things like that. But I think it's quite intriguing that this sort of gives you sort of just the right amount of water, right? It doesn't give you too much water, which we think may be problematic from sort of an origins of life point of view. And it also doesn't give you no water. It sort of gives you a couple of Earth oceans, or maybe 10 Earth oceans, which I think would be, you know, a good thing. Yeah.
What are your thoughts on, did the Earth
go through a phase? Sorry, I think we
Yeah.
need to go. But did the Earth go through a phase, you feel, where there was an envelope? I mean, I see your orange line sort of goes near 1-1,
Yes.
you know, so is that what you're
The
saying?
answer is yes, and that's the very last part of my talk.
Oh, okay, oh, forgive me.
No, I think it's great you're asking
That's
this.
a different way of making your association.
Exactly.
Okay.
Yeah, that's what I'm gonna tell you what I think, and then you can see what you think, and then we can have a discussion about it. Yeah.
Great.
And Robin.
This might also be a question that just leads on into the next part of the talk, but so you've got 2 things which are changing by an order of magnitude there. One
Yes.
is staying flat. What's the feedback to keeping the atmosphere, ocean constant, H2O constant through changes in planet mass of an order of magnitude, roughly?
I think it must be the interplay between the solubility and the pressure. I don't think there's like a fundamental reason why it should be constant. It just happens that they balance out. Yeah.
It's a 1980s Japanese paper I'll forward to you.
Yes, but I think that's about their metal phase, right? That's where the atmosphere. So it depends how you produce the water. I think the Japanese paper that you're referring to does it through interacting with iron melt. Yes.
We can
Yeah.
talk about that.
But in this case, we also produce actually water through, because we can exclude iron metal from all the reactions, and you still produce a couple of % water. With the difference is that the silicate phase absorbs more of the water from the iron core. So you do have multiple mechanisms in producing the water. And actually you can understand the silicate magma ocean interactions, like the magma ocean hydrogen interaction producing the water quite easily, because what's really happening is you evaporate the magma ocean into the envelope, And so you form basically Si and O or O2, and it's basically the O that's interacting with the hydrogen, making the water this way. So there are two pathways, two distinct pathways of making the water. Yeah. So that's why it's slightly more complicated than just, I think, the trade-off with the ion. Yeah. Okay. This is for Dave. You asked an extremely good question because I have some slides to answer you. Okay, so I thought after all this exoplanet talk, right? I think the obvious question is always like, but how about Earth? Like, how does Earth fit in? Were we really some weird outliers, or maybe we can start learning something about Earth formation from the exoplanets? And I think for me, that's the fun part, how we're starting to have the synergy between these two different fields. So did Earth, or was Earth shaped by a primordial hydrogen envelope? So I don't think Earth itself, because we have very good evidence that Earth itself was assembled through a phase of giant impacts. So I don't think the Earth as a whole size embryo, it created a hydrogen dominated envelope. But the embryos that formed the Earth, I think they may. And I think that's the question I would like to look into. So what's the evidence? Some are the clues that we have for Earth formation. Okay, so one piece of evidence that I skipped over so far is even Earth does have something what we call a core density deficit. So even for Earth, our iron core is actually not as dense as you would expect if it would be pure iron. How do we know that? Very nice. You know it from seismology, basically. You can measure the velocity of the seismic rays, and so you can basically estimate the density on the inside. And so it's underdense. So it's not just iron. We don't know what else it is. So everyone has their favorite element. Carbon is often cited, silicate, oxygen, hydrogen. So actually, Dave Stevenson already pointed out in 1977 that you would only need 1% in mass of hydrogen to explain the entire it's almost 8% or so of the Earth core density deficit. So hydrogen is a candidate, but it's not the only one. Anything lighter than iron, basically in the right proportion, would give you this result. But nonetheless, so one thing to explain. Then we have helium and neon isotopes that we measure in the Earth. So particularly the neon 20 to neon 22 ratio suggests that some signature of nebular gas accretion, so that somehow there is an imprint on the Earth today from the nebular chemistry in the neon isotopes. So, okay, some hint that there's maybe some memory. And then last but not least is related to Mars. So, Earth generally is thought to have formed by the assembly of, 5 to 10 embryos that were the size of Mars or bigger and that had this phase of giant impacts, right? The last one probably formed our moon. That's generally what we think. And we know both from formation models, but also from directly age dating Mars with a half-in tungsten system, that Mars forms in around 3 million years. So 3 million years is interesting because that's roughly the typical disk lifetimes that we know from doing surveys of disks around stars, but it's also what Roger told us, I don't know where he is, from dating the nebular magnetic field. So it's like an interesting number. So maybe the embryos that formed the Earth were exposed to the original nebula and maybe could have had some imprint of this interaction with a hydrogen. So I already told you, you need to be big enough to hold on to any gas. So, and at 1 AU is just the size of Ceres. So if I'm Mars sized, that's good. So that condition is fulfilled. So you can have in couple of, or maybe a Mars sized embryo would be big enough to hold on to the hydrogen. So it can have an envelope, but it's not enough, right? To have any interesting chemical signature that then we could preserve over time, the hydrogen has to be in contact with the molten magma ocean, right? So if we just stick a hydrogen envelope on Earth today, nothing interesting will happen, mostly. Well, hydrogen is very explosive, so you have to be careful with that statement, but you know what I mean. So you also have to actually satisfy the criterion that you can hold on to the hydrogen while the interior is still hot enough to have a molten magma ocean. And if you add this, then just being Mars in size is not quite enough. So if you would heat up a body of Mars to a temperature at which you have a magma ocean, let's say, I don't know, 1,800 Kelvin, or you can pick your number, I don't really care that much. That would become unbound, like gravitationally, you can't overcome this. But if you become twice the mass of Mars, roughly, you couldn't be both hot enough and massive enough to hold on to the hydrogen envelope. Okay, so because the key is, right, the hydrogen has to be able to chemically interact with the molten magma. And if you make the planet too hot, and if it's too small, then by transferring the temperature to the envelope, that envelope will just become unbound and run away. So not much interesting things can probably happen. So this is where this constraint comes from. So if the embryos that formed Earth were a few times, let's say twice at least, the mass of Mars, then we can have an interesting sort of chemical exchange between the envelope and the magma ocean. And so this is basically this calculation that we did. And this is what we found. So one of the things that we looked at is the core density deficit. And so this is the Earth here, and this is the hydrogen mass fraction that you would need. So this is 0.2%. To explain, after you allow for the global chemical equilibrium, to explain the Earth's density, core density deficit, which is about 9%. And the composition of the core would be 0.5% in hydrogen, 0.8% in oxygen, 3.8% in silicate, and 95% iron. So you can explain it, right? It's maybe not a big surprise, right, after we had the previous result, but so if the embryos could have accreted like less than 1% of hydrogen, you could explain the Earth density deficit. Okay, fine. What really made this problem interesting to me is that the same model also produces basically a few Earth oceans worth of water. So right, it's not a different model, it's the same outcome. So now again, you ask, where's the water? How much do you produce? And this is the water in the silicate. This is the water in the atmosphere. And you get a couple of oceans worth of water. I think in this model, we got like 5. We since redid all these models accounting for non-ideality, because some people thought it was really very important, but the results are very similar. You get a little bit more water, but I think all consistent with how well we can determine the amount of water we have on Earth. So now you can explain with one model, both the amount of water we have on Earth and the core density deficit. Is there anything else? So the last thing we looked at was just the bulk oxidization state of the Earth, which my colleagues like to call oxygen fugacity. All it's really telling you is how reducing or oxidizing the bulk planet is. And that too, this model would explain quite well. So going from very reducing conditions in the original solar nebula and actually the chondrites to something that's consistent with sort of bulk Earth. So all this is to say, did this actually happen? I don't know. But I think it's intriguing that you can explain sort of 3 pretty fundamental facts about Earth's properties that usually people have explained in the past by one model for each, right? So there's loads of work that's been dedicated to the delivery of water on Earth, often very painstakingly trying to explain an exact D/H ratio, for example. Actually, this model can also explain the increased deuterium to hydrogen ratio because the lighter hydrogen is the one that's partitioned into the core, into the metal phase. So you would leave the heavier hydrogen or the deuterium in the water. Again, I don't think it's proof, but at least sort of hangs together. Similarly, a lot of work has been done explaining the oxidation state of the bulk Earth from formation and the core density deficit. There are many candidates. But what I personally find intriguing, and I really don't know if that's what happened, is that it sort of all hangs together. It's like one model that gives you these 3 features. And then as a very last thing, because I do want to leave some time for questions, is for me, the most rewarding part of this project was that somebody called me up after we published this paper and said, you know, we will know. We will know if this is really what happened and if Earth really has 1% or 0.5% of hydrogen in the core. And I'm like, really? How? They said, oh, we're already collecting the data. So how will we know? So the good thing is, you know, we don't need to speculate. We don't need to argue. We can just wait. So how will we know? From neutrinos. So basically, atmospheric neutrinos is so ingenious. I love this. The interplay of like astrophysics and planetary, like it's beautiful. So atmospheric neutrinos, when they, you know, are produced by high energy radiation hitting the atmosphere, you produce neutrinos that travel through the Earth. As they propagate through the Earth, as you know, neutrinos can change flavor. But the rate at which they change flavor depends on the neutron to proton ratio in the core. And hydrogen, as you know, is special because it doesn't need the neutron in the core. And so you have a different neutron to proton ratio as a result, and therefore you get a different amount of neutrinos oscillating or fluctuating between the different states. And it's basically just a question of getting enough atmospheric neutrinos. So we're already collecting the data. Actually, people have been doing this for 10 years. And in roughly another 5 to 10 years, we will have enough data to know. We will just know. So I think that's just a very cute, for me, this was the most fun part. So stay tuned. We can like reevaluate all these ideas in sort of 5 to 10 years. Okay, with this, I think I flooded you with a lot of information. Maybe I will just leave up my summary here. I think the one take-home message that I would like to part with is like loads of interesting things are happening inside planets, and they are much more dynamic. And we need to sort of do models that include both chemistry and physics, and we have to move away from just being physicists, at least for me, I guess I can say for myself. I can no longer just be a physicist to understand planets and their interpretation and formation. I think there is a big part in terms of chemistry that we also need to account for. So with that, I will stop here and happy to take more questions.
Okay. All right, great. So more questions. All right, let's start here.
Okay. This could be a very naive question because I don't do this stuff. But assuming your model and assuming population properties of planets that we know, or you know, can you predict how many Earths there are there?
How many Earths?
Yeah.
I
mean,
yeah, so that depends. Do you mean in terms of chemical composition, in terms of mass, in terms of distance from the star? How do you, when do we define some?
where we can have life?
Okay, I don't think I can predict that. I think a lot of this work, though, is motivated by that, because I think, for me at least, by trying to really understand the processes of planet formation, how you put together a planet, I'm hoping it will provide useful input in one day that we'll be able to say how many Earth we have. I don't think we truly know yet. We can estimate it observationally. I would say, I don't know, Dave, correct me, I would say 10% is maybe 10 to 20%, but it's like I think we're still sort of in the learning phase of putting the pieces together. So I think one part, is the formation, at least for me in the chemistry, if you can, I would say, at least for me personally, I think the chance of finding a habitable planet, for me at least, has gone up, because I think like getting like a few oceans worth of water, if that's one thing you need, I think seems to be like a default for these super Earths. So to me, this seems like a good thing, but I don't know, we will see. It's all very new, we're still really learning, I feel, in this area.
Great. Okay, I'll just sort of walk around the room. So
Perhaps one of the happy things a theorist can have, I'll not use the word kill, but to eliminate the need for somebody else's theory. So does this mean that we no longer need the formation of the Earth's ocean by accretion of comets at the late stage?
Yes. I will say, I think there is some evidence from the xenon isotopes that there, I think, was some loss and probably some late accretion, but it doesn't have to be the bulk, and it doesn't have to be, it's not needed to explain the water button yet.
Yes. I'm trying to choose which one. I'll start.
Oh,
I'll save your time to go back.
So if we think about how the Earth formed versus how mini Neptunes formed, I presume the super Earths just come from mini Neptunes. Do you think that the mini Neptunes also form basically through this stage of Mars-sized embryos colliding? It's just that it happened fast enough that they then got to accrete through the second primary atmosphere, so they really had two of them? Is that how we should think about it?
Probably, but I actually do not really know the answer because so I think as long as those mergers happen while the disk is around, it's okay because you would recreate the primary envelope, and sort of from naive planet formation theory, that would be the obvious thing I would tell you. But I'm not sure I could prove it to you unambiguously. Yeah.
Well, would your models, like if you get through twice, would that in any way impact what you would expect for the interior?
Yeah, so not in the simple global chemical equilibrium because you reset everything. I think once you really start worrying about transport and mixing, maybe. But I personally think that giant impacts typically are so energetic that you get pretty good mixing, at least if you have several of them. So probably not, but worth thinking about. Yeah.
I'll take my second one if there's time.
Yeah, so your point about formation of water in situ makes us maybe more hopeful about the Rockies around end dwarfs and presence of atmospheres.
Yes.
So far, we're not finding much. Do you want to comment on that and where you think that intersects with this chemical equilibrium stuff in the sub-Neptune phase?
You mean in the sub-Neptunes or in the super?
Yeah, you can form a planet with an envelope, and it will also form a bunch of water through chemical equilibrium.
Yes.
And then you lose the envelope.
Yes.
Do you think with the Rockies that we're seeing the airless so far, it's just been so extreme, the loss processes that it's driven off everything, or?
Yeah, that's a great question. So this is of course not the end state, as you know better than anyone else. So depending on the equilibrium temperature, the water can rain out, so it doesn't need to stay in the envelope. And embryos are actually very good examples of that because they're cooler. So in some cases, I think you may just not see it because it's not in the gaseous phase. But there's also as you know, loss process over time will continue. So you can break up the water, as you know, photochemically. And so then you wouldn't see it because of that. So I don't think this is necessarily the final state. So there are more processes going on. I also have some thoughts on why there are so many flat spectra, and I think not necessarily it means there are no envelopes, but I think it could just be some high patchy latitude clouds. We can talk about that some more. But yeah, it's intriguing, but I think don't know yet what to make of it. Yeah.
Okay, Roger.
Yeah. So once
we're joined from numerous professors from urban planetary science. Wonderful.
What I was say. Yes.
And concentrators and activists, but that's a separate. Sorry.
Once the core forms, right? Do you expect there to be more equilibration between the core and the mantle throughout the next 4.5 billion years of history, or is the composition you have going to be stable through time?
So we assume that it continues to equilibrate as long as you're hot enough. Once you can solidify the magma ocean or form a crust or get anywhere near that, we naively just say, okay, that's the frozen state. Again, reality will be much more complicated, but it's like a first step trying to get to roots of this problem.
So is the core mantle boundary frozen in, or is there still
the core mantle boundary? You mean frozen in locally or
can hydrogen still get out of it?
So I personally suspect that what's truly in the metal phase probably will stay there and it's hard to get out. But I think the silicate have a better chance for the hydrogen, coming back to the surface, both through like plate tectonics, volcanism, but also just through exchange for longer. But that's just my intuition.
Dimitar?
Well, Roger asked my question, but now that you said that, what is your intuition based on that hydrogen will be trapped in the core? My intuition is that it will leave the core.
It's because actually for hydrogen and metal, we actually do have pretty good experimental lab data. And so I think basically it forms a really nice lattice and it's a very small molecule and can be nicely trapped in that, I forget these iron core structures. There's different ways for iron to exist, but I think it shows that it it seems quite happy there. It is siderophile, so it's iron loving, so I think it's quite happy there. So that's why I think it probably stays on the metal phase.
Okay, well, we're at 2:30, so we're gonna cut it off there. But we have the pleasure of your company through most of the day tomorrow, and let's please thank Professor Schlichting.
Yeah.
Great.